Somewhere, right now, in a bedroom that looks almost exactly like yours, an alarm is going off. A hand reaches out in the dark, and for about half a second, before the thumb even touches the screen, there are two futures sitting on top of each other in the exact same space. One where the thumb hits snooze, one where it doesn't. You've lived this moment 1,000 times and never once thought about it as anything other than a small, forgettable decision. But what if I told you that physics, real physics, the kind that gets tested in labs and used to build the phone that alarm is going off on, has something to say about that half second that most people never hear? What if both things happen? Not might happen. Not could have happened if things had gone differently. Happen actually happen, in the same sense that the version of you reading this sentence right now is actually happening. Stay with me on this one, because by the end of tonight, the idea of the choice you didn't make is going to stop sounding like a figure of speech and start sounding like something with actual physical weight behind it. Before we go further, if the kind of question that makes you stare at the ceiling a little longer than usual is the kind of thing you're here for, go ahead and subscribe, and if you've got a second, drop a comment telling me what decision you made today that you're still turning over in your head. Because I want to know what's on your mind while you listen to this. Think about how many of these moments you've already lived through without a second thought. The pause before you replied to a message, thumb hovering, the words already typed out, deleted, retyped. The extra few seconds at a green light before you decided to turn left instead of going straight home. The breath you took right before you said something you couldn't take back, or didn't say the thing you now wish you had. Every one of those moments felt, at the time, like a single point where you stood still and the universe waited for you to choose. And every one of them passed the exact same way this alarm clock moment is about to pass. One outcome happened, the other one, whatever it was, simply stopped being talked about, filed away under the heading of things that didn't happen, treated as though it evaporated the second you didn't pick it. Tonight we're going to take that evaporated option and ask, with the full weight of modern physics behind the question, whether it actually evaporated at all, or whether it's sitting somewhere right now. Just as solid, just as real, just as lived in as the version of today you're currently experiencing. Now let's get into it. Here's the assumption almost everyone walks around with, so quietly they don't even notice they're carrying it. We assume there is one timeline, one version of events. You made a choice this morning, you made a different choice yesterday, and somewhere in your head there's a ghost of the other option, the version where you said yes instead of no, where you took the job instead of staying, where you sent the text instead of deleting it. We treat that ghost as pure imagination, a story we tell ourselves. Not real in any sense that matters, just a shape our regret or our curiosity likes to draw in the air. And there's a good reason we assume that, because from the inside, from where you're sitting, there is only one thread. You don't remember the version of you that stayed home. You don't have a memory of the text you didn't send. All you have is this. One continuous, unbroken line of experience, one version of today, one version of your life. So it feels obvious, almost too obvious to question, that this is the only version that exists. But notice what that conclusion is actually built on. It's built on the fact that you can't see the other version. Not on any evidence that the other version doesn't exist. Those are two completely different things, and the entire rest of tonight is going to live in the gap between them. Think about a river for a second. one of the big, slow ones that spreads out near its delta, before it finally reaches the ocean. From high above, in a photograph taken from a plane, that river doesn't look like a single clean line. It looks like a braid. Dozens of channels splitting off from the main current, wrapping around sandbars and islands, some of them rejoining further downstream, some of them drying up entirely, some of them carrying most of the water, while others carry almost none. If you were a single drop of water sitting inside that river, you would never experience the braid. You'd only ever experience the one channel you happened to be moving through. From your perspective, as that drop, there would be exactly one path, one river, one story. Because a drop of water can only ever be in one channel at a time. But zoom out to the aerial photograph, and the single path you experienced turns out to have been one thread inside a much larger, branching structure the whole time. A structure that was there before you noticed it, and would have been there whether or not you ever looked down and saw it. That's the entire shape of the argument tonight is built on. Not that there's some invisible parallel world floating alongside ours in a separate place, the way it gets portrayed in movies, with a shimmering doorway between them. But that the single channel you're experiencing right now, this one continuous thread of your life, might be exactly like that single drop of water, real, completely, fully real. And also, at the same time, just one strand inside something considerably larger than what you can see from where you're floating. Keep that image of the braided river in the back of your mind, because we're going to come back to it more than once tonight. And each time we do, the braid is going to turn out to be wider and stranger than it looked the last time you glanced at it. To understand why physicists take the other option seriously, and I mean seriously, not as a thought experiment for a philosophy class, but as a live, debated, mathematically grounded possibility, we have to go back to an experiment that is almost embarrassingly simple to describe and almost impossible to fully explain even today, even to the physicists who run it for a living. It's called the double-slit experiment, and if you've never had it explained properly, what I'm about to tell you is going to rearrange something in your head. Picture a wall with two thin vertical slits cut into it, side by side, close together. Behind that wall, a second wall, a screen set up to catch whatever passes through. Now imagine you're firing something at the first wall. Tiny grains of sand, let's say. Some grains hit the wall and stop. Some pass through slit 1, some pass through slit 2. On the screen behind, you'd see two bands, roughly lined up with the two slits, because that's just where the sand landed after going through the gaps. Nothing strange about that. That's exactly what you'd expect from anything solid, anything that behaves like a little object flying through space. Now replace the sand with light. This experiment was first done over 200 years ago by a scientist named Thomas Young in 1801, using nothing more exotic than sunlight, a couple of slits, and a piece of card. And when he ran it, he didn't get two bands. He got a whole pattern of alternating bright and dark stripes, dozens of them, spreading across the screen like ripples. That pattern is called an interference pattern, and it's the signature of a wave. Think about what happens when you drop two stones into a still pond at the same time. The ripples spread out from each stone, and where two ripples meet, they either add together and make a bigger wave, or they cancel each other out and the water goes flat for a moment. That's interference. And that's exactly what light was doing, passing through both slits at once as a wave and interfering with itself on the other side. Fine, light is a wave. That was a strange enough discovery for 1801, but the story doesn't stop there, and this is where things stop being merely strange and start being genuinely disturbing. Because a century later, physicists discovered that light also behaves like a particle. Individual packets of energy, called photons, that hit a detector one at a time, like tiny bullets, not like a continuous wave at all. So which is it? A wave or a particle? The honest answer, the answer that took decades of the smartest people alive fighting about it to arrive at, is both, and neither, depending on how you ask the question. And here's where the double-slit experiment gets truly strange. What happens if you fire the photons one at a time? Not a beam of light, not a flood of particles all at once, but one single photon, waiting a moment, then another single photon, one after another, thousands of times, patient enough to let each one arrive on the screen alone before sending the next. Common sense says each photon has to go through one slit or the other. It's one particle. It can't split itself in half. So you'd expect, over time, as thousands of individual photons build up a picture on the screen, to see exactly what you saw with the sand. Two bands, one behind each slit. Instead, you get the interference pattern again. Stripes, ripples. The signature of a wave. Built up one particle at a time by individual photons that were each fired completely alone, with no other photon anywhere nearby to interfere with. Sit with that for a second, because it's not a rounding error and it's not a trick of the equipment. Each individual photon, alone, with nothing else in the apparatus to bump into, behaves as though it went through both slits at the same time and interfered with itself. As though, for that photon, there wasn't one path through the wall. There were two, simultaneously, and both of them were real enough to leave a mark. Now here's the part that turns this from strange trivia into the doorway for everything we're going to talk about tonight. Physicists, understandably, wanted to catch the photon in the act. They wanted to know, for real, which slit it actually went through. So they set up a detector right at the slits to watch. Just observe. Not interfere, not block anything, just watch which slit each photon passes through. And the moment they did that, the interference pattern vanished. The stripes disappeared. The photons started landing in exactly two bands, one behind each slit, behaving exactly like the sand, exactly like ordinary particles going through one hole or the other. The simple act of looking, of gaining information about which path was taken, collapsed the wave-like behavior into ordinary particle behavior. Turn the detector off, and the stripes come back. Turn it on, and they vanish. This has been repeated, refined, and confirmed for over a century, with electrons, with atoms, even with molecules made of dozens of atoms bonded together, and it never fails to hold. Reality itself appears to behave differently depending on whether information about which path exists anywhere in the universe observed or not. This is not a metaphor for a video script. This is one of the most well-confirmed, most repeated results in the entire history of experimental physics, and it is also one of the most unsettling. Because it means that before that detector is switched on, the photon isn't taking one path and hiding it from us. It is, in some real physical sense, taking both paths at once. And whatever both paths actually means underneath the math, it's the exact same underlying mystery as the question we started with tonight. Whether there's really just one version of events, or whether underneath the single thread you experience, there's something branching that we simply can't see from where we're standing. This duality wasn't confined to light either, which is part of why physicists couldn't simply write it off as some quirk of photons specifically. In 1924, a French physicist named Louis de Broglie proposed, as part of his doctoral thesis, that if light, which everyone had assumed was purely a wave, could behave like a particle, then matter, which everyone assumed was purely made of particles, should be able to behave like a wave too. It sounded outlandish enough that his examiners weren't sure whether to pass him, and reportedly sent the thesis to Einstein for a second opinion before granting the degree. 3 years later, in 1927, experiments confirmed it directly, firing electrons, which had always been treated as small, solid, particle-like objects, at crystal structures, and watching them produce the exact same kind of interference pattern that light produces. Electrons, protons, entire atoms, all of it carries this same dual nature. And in that same year, 1927, the German physicist Werner Heisenberg formalized something called the uncertainty principle, which states with real mathematical precision that there are pairs of properties, like the exact position of a particle and its exact momentum, that cannot both be known with perfect precision at the same time, not because our instruments aren't good enough, but because the particle itself doesn't possess both values with perfect precision simultaneously. The more precisely you pin down where something is, the less precisely its momentum is even defined, as a matter of physical fact, not measurement error. This is the same underlying strangeness we saw in the double-slit experiment, showing up from a different angle, and it's part of why, by the late 1920s, the physics community had run out of ways to pretend the quantum world was just the familiar world of billiard balls and waves, only smaller. It clearly wasn't. It was something genuinely new, governed by rules that don't have a clean analogy in ordinary experience, and physicists needed a way to talk about this both at once state without just throwing up their hands, and the tool they built is called superposition. A quantum object, before it's measured, doesn't have to be in one definite state. It can exist as a genuine mixture, a real physical combination of every state that's possible given the situation, all layered on top of each other, until something forces the situation to resolve into a single, definite outcome. This isn't the physicist saying we don't know which one it is yet. It's the physicist saying the object itself, prior to measurement, is actually in all of them, in a way you can write down with precise mathematics and use to predict experimental outcomes to unbelievable accuracy. And to make this idea sit in your gut instead of just your head, there's a thought experiment that has become so famous it's practically wallpaper at this point. But almost nobody actually understands what its inventor was trying to say with it, because the popular version has gotten the point almost exactly backwards. It's Schrödinger's cat, and it was dreamed up in 1935 by the Austrian physicist Erwin Schrödinger, and here's the setup exactly as he framed it. A cat is sealed inside a steel box, along with a small amount of a radioactive substance, a Geiger counter to detect radioactive decay, a hammer and a flask of poison. If the Geiger counter detects a single atom of the radioactive substance decaying, a random quantum event with no fixed timing, it can happen this second, or an hour from now, it triggers the hammer, which shatters the flask, which releases the poison, which kills the cat. The radioactive atom, before you check on it, is in a superposition. It has both decayed and not decayed. In the same layered, simultaneous way, the photon went through both slits. Now here's where it gets uncomfortable, because that superposition is wired directly into the fate of the cat. If the atom really is in a superposition of decayed and not decayed until it's observed, then logically, so is the cat. Alive and dead. At the same time. Not we don't know which, but actually, physically, both, sealed inside a box you haven't opened yet. Schrödinger did not propose this thought experiment because he thought it was a fun way to imagine quantum weirdness. He proposed it because he thought it was absurd, a reductio ad absurdum. His way of saying, look how ridiculous this gets when you take the equations at face value and scale them up from a single atom to something the size of a cat. Something's got to give, he was arguing. Either quantum mechanics doesn't really work the way the equations say, or something about the boundary between the tiny quantum world and our large everyday world needs a serious rethink. For most of the 20th century, the answer most physicists gave was something called the Copenhagen interpretation, developed largely by Niels Bohr and Werner Heisenberg in the 1920s. The Copenhagen view says, in effect, don't ask what's happening while the box is closed. The mathematics only describes probabilities of what you'll see when you open it. The act of measurement, of observation, causes what's called a collapse of the wave function, an actual, instantaneous, physical snap from superposition of everything possible down to one single definite outcome. Before you open the box, the question which one is real is not just unanswered. Under Copenhagen, it's treated as meaningless. Only the measurement is real. Everything before it is potential. This wasn't a quiet academic disagreement either. At the 5th Solvay Conference in Brussels in 1927, a gathering that brought together nearly every major physicist working at the time, Albert Einstein and Niels Bohr began a running argument over exactly this question that would continue, in letters and conferences, for the rest of their lives. Einstein never rejected the mathematics of quantum mechanics. He rejected the idea that the mathematics was the whole story, famously insisting that God does not play dice with the universe, that there had to be some deeper, hidden layer of reality beneath the probabilities, some set of facts we simply hadn't discovered yet that would restore a single definite state to every particle at every moment. Bohr pushed back just as hard, arguing that Einstein was smuggling in an assumption. The assumption that particles must have definite properties even when nobody is measuring them. An assumption quantum mechanics gave every reason to abandon. Neither man ever fully convinced the other, and in a strange way, the argument itself became part of the culture of the field. A genuinely open wound in the foundations of physics that most working scientists learned to work around rather than resolve, because the equations, whatever their proper interpretation, kept making extraordinarily accurate predictions regardless of which side of the debate you personally believed. That answer worked well enough to build the entire technological world you're living in right now. From the phone in your hand to the GPS satellite that knows where you are. And it earned generations of physicists a comfortable working relationship with quantum mechanics. But it left one enormous itching question sitting right at the center of the theory. One that a lot of physicists were quietly uneasy about for decades. What actually counts as a measurement? Where exactly does the collapse happen? Is it the Geiger counter that collapses the wave function the instant it detects the decay? Or is it the hammer? Or the poison? Or the cat's own nervous system the instant the poison reaches it? Or is it you, the observer, the instant you open the box and look inside? Nobody could point to a physical mechanism, a specific interaction, a specific threshold where a fuzzy superposition suddenly and forcibly becomes one single, sharp, definite fact. The equations of quantum mechanics themselves describe a smooth, continuous, gradually evolving wave function, with no collapse built into them anywhere. The collapse was added on top, almost as an extra rule bolted onto the theory, because without it, the theory seemed to predict cats that are simultaneously alive and dead, and that seemed obviously wrong. But bolting a rule on top of a theory because the alternative feels too strange is not the same as explaining anything. And in 1957, a young physicist at Princeton working on his doctoral thesis decided he was done accepting that patch job. His name was Hugh Everett III, and the question he asked was disarmingly simple. What if there's no collapse at all? What if the equations of quantum mechanics are simply telling the truth, the whole truth, with nothing extra bolted on, and what actually happens is this. When the Geiger counter interacts with the radioactive atom, the counter itself becomes entangled with the superposition. It doesn't force a collapse. It splits into two versions, one that detected decay and one that didn't, both fully real, both continuing to exist, just no longer in contact with each other. When the hammer and the poison and the cat get pulled into that interaction, they split too. Live cat, dead cat, both real, both physically existing, simply in two branches of reality that have separated from one another and can no longer interact or exchange information. And when you, the observer, open the box, you don't collapse anything either. You split too. One version of you sees a live cat. One version of you sees a dead cat. Both of those versions are completely real, completely convinced they are the only version, and from that moment forward, they simply never meet again. Everett's idea is now known as the many worlds interpretation, and when he first proposed it, it was met with something close to open hostility. Niels Bohr, by then the towering, almost priest-like authority on how to think about quantum mechanics, reportedly dismissed it outright. Everett travelled to Copenhagen in 1959, hoping to defend his thesis to Bohr directly. And the meeting went badly. Bohr and his colleagues treating the young American's idea as naive at best. Discouraged and increasingly frustrated with academic physics, Everett left the field entirely not long after finishing his doctorate. He went to work for the Pentagon, doing classified operations research and nuclear targeting analysis. Brilliant, private, and by most accounts a heavy drinker who chain-smoked and worked odd hours. A man who had, in his own telling, solved one of the deepest puzzles in physics and watched almost the entire physics establishment shrug at it. He died of a heart attack in 1982 at 51 years old, having spent the last decades of his life almost entirely outside of the field where his single most important idea lived. What makes Everett's story land even harder is that he never seemed to fully abandon the conviction that he'd been right. Colleagues who knew him during his Pentagon years described someone who would occasionally, almost offhandedly, bring up his old thesis in conversation, half joking that immortality was guaranteed under his own theory, because in a branching multiverse there is always some branch, however improbable, in which any given person survives any given event, which meant that from the inside you could never actually experience your own death, only ever experience surviving. It's a genuinely strange thing to sit with. A man who built one of the most important ideas in the philosophy of physics watched it get dismissed by the people whose approval mattered most, and then went on decades later, still privately reasoning about his own mortality using the very framework the physics establishment had shrugged off. The theory itself didn't just sit forgotten, though. It got a second life, and a name thanks to a physicist named Bryce DeWitt, who around 1970 started writing about Everett's old thesis and gave it the label that stuck, the many worlds interpretation, a phrase Everett himself hadn't used. DeWitt's articles reintroduced the idea to a new generation of physicists who were, by the 1970s and 1980s, growing increasingly uncomfortable with the unexplained collapse at the heart of the Copenhagen picture. And slowly, unevenly, over decades, the idea moved from something whispered about at the edges of the field to something taken seriously enough to be defended in mainstream journals and taught in graduate seminars. It wasn't until years after his death, as physicists began taking the foundational problems of quantum mechanics more seriously again, and as a new generation started asking, quite reasonably, why we should bolt an unexplained collapse onto a theory that works perfectly well without one. That Everett's idea moved from academic curiosity to one of the leading, seriously debated interpretations of quantum mechanics that exists today. It is not universally accepted. There is no consensus, and there may never be one. Because this is one of those rare places in physics where multiple interpretations make the exact same testable predictions, and the disagreement is genuinely about what's actually happening underneath the math rather than about what we'll observe in an experiment. But it is taken seriously by a substantial number of working physicists, discussed at major conferences, defended in serious journals, and taught in graduate courses. Precisely because it removes the single strangest, least explained piece of the old picture, the mysterious, mechanism-free, never-defined moment of collapse. Under many worlds, there is no collapse. There's only branching. Continuous, constant, physically real branching, governed by the exact same equations that already describe everything else in quantum mechanics, with nothing extra added and nothing taken away. There's an obvious objection that probably just occurred to you, and it's the right objection to have, because it's the same one physicists raised against Everett almost immediately. If there really is a version of you that saw a live cat and a version that saw a dead cat, why don't you ever bump into the other version? Why doesn't the universe feel like it's constantly splitting into parallel copies that occasionally cross paths, the way it does in science fiction, with alternate versions of people meeting each other in diners or fighting each other in alleyways? The answer is a process called decoherence, and it's one of the most important concepts in this entire conversation, because it's the thing that explains why the branches, once they separate, don't just stay separate, they become permanently, physically incapable of interacting again. Not because of some rule someone wrote down, but because of ordinary physics doing exactly what it always does. Think about it this way. When two waves are perfectly aligned, in step with each other, they can interfere. The way the ripples from Thomas Young's two slits interfered to build those stripes. But interference only works cleanly when the waves stay coordinated, when there's nothing scrambling their relationship to each other. The moment a quantum system, like our radioactive atom, interacts with something enormously complicated, like the trillions of air molecules in the box, or the countless atoms making up the cat's body, or the light bouncing around inside, that interaction spreads the information about which branch this is out into an almost incomprehensibly large number of other particles. Once that happens, recombining the branches back into something that could interfere with itself again would require somehow gathering up and perfectly reversing the state of every single one of those particles. An amount of precision so far beyond anything physically achievable that it might as well be impossible. Not impossible in principle, in the sense that the math forbids it, Impossible in the same practical sense that it's not impossible in principle for all the air molecules in a room to spontaneously rush into one corner and leave you gasping for breath in what's left. The laws of physics don't forbid it. The odds are so astronomically small that it will, for all practical purposes, never happen in the lifetime of the universe. This is why the branch containing a live cat and the branch containing a dead cat, even though they split from the exact same original event, immediately become causally sealed off from one another, drifting apart into what are effectively two separate non-interacting versions of reality. Even though nothing physically moved anywhere, no wall appeared, no space stretched. They simply stopped being able to talk to each other the instant the information leaked out into their surroundings, in the same overwhelming, statistically irreversible way that a drop of ink diffusing into a glass of water will never reassemble itself back into a single, concentrated drop. Decoherence isn't a hypothesis waiting around for confirmation either. It's been measured directly, repeatedly, in laboratories around the world. In 1999, a team led by physicist Anton Zeilinger fired entire molecules, Buckminster fullerene, soccer ball-shaped cages made of 60 carbon atoms bonded together, through a version of the double-slit experiment, and got the same interference pattern that Young got with sunlight almost 2 centuries earlier, proving that superposition holds even for genuinely large, complex objects, as long as decoherence hasn't yet had the chance to leak their witch path information out into the surrounding environment. Separately, physicists have directly measured decoherence happening in real time, watching a quantum system's ability to interfere with itself fade away, smoothly and predictably, exactly as fast as the equations say it should, as the system becomes increasingly entangled with the atoms and photons around it. So decoherence isn't a convenient answer physicists invented to patch the hole in Everett's picture. It's an experimentally confirmed, mathematically precise process that was already sitting inside quantum mechanics, waiting to be taken seriously. And it does exactly the job that used to be pinned on the mysterious, mechanism-free idea of collapse, except this time with an actual explanation for why it happens and how fast it happens. And the buckyball experiment isn't even the most striking demonstration of how far this scales up. In 2010, a physicist named Aaron O'Connell, working at the University of California, Santa Barbara, managed to put a tiny mechanical resonator, a paddle-shaped sliver of metal about the width of a human hair, small enough to see with the naked eye if you knew exactly where to look, into a genuine quantum superposition. The paddle was cooled down to a fraction of a degree above absolute zero, cold enough to strip away almost all ordinary thermal vibration, and using a specially designed circuit, O'Connell's team managed to get the entire object into a state where it was, in a real and measurable sense, both vibrating and not vibrating at the same time. Not an atom, not a molecule. An object large enough that under different circumstances you could have pinched it between 2 fingers. That experiment was named the Breakthrough of the Year for 2010 by the journal Science, precisely because it demonstrated that there's no known point at which quantum superposition simply stops working as things get bigger. There's no line drawn anywhere in the laws of physics that says objects below this size can be in 2 states at once, and objects above this size can't. The only thing that determines whether superposition survives is whether decoherence has had the chance to happen yet, whether the object has been sufficiently isolated from the noisy, information-leaking chaos of its surrounding environment. Your brain, warm, wet, densely interconnected, and constantly exchanging information with its surroundings, is about as far from that kind of isolation as a system can get. Which is exactly why the branching happening inside it decoheres essentially instantly, splitting into separate, non-interacting versions of you so fast that neither version ever has the slightest chance of noticing the other. One existed. So let's actually sit with what branching means, because it's easy to hear that word and picture something rare and dramatic. A fork in the road that only happens during some exotic laboratory experiment with cats in boxes. It is not rare. It is happening constantly, at a scale that is genuinely difficult to describe in ordinary language, and it's happening inside you, right now, while you listen to this. Every single quantum interaction, every time a particle of light hits a molecule, every time an electron in an atom absorbs or releases energy, every time a radioactive nucleus decays or doesn't, every subatomic event anywhere that has more than one physically possible outcome is, under this picture, a branching point. And your body is not somehow exempt from quantum mechanics because it's large and warm and made of trillions of cells. It's built entirely out of the same particles that behave this way in a lab. The physical process that lets your eyes detect light involves individual photons striking individual molecules in your retina, quantum events, each one a branching point. The physical process that lets a nerve fire involves ions moving through channels that are themselves governed by quantum tunneling. A phenomenon where a particle has some probability of passing through a barrier it classically shouldn't be able to cross at all. The radioactive decay of carbon atoms happening in your own body right now, because a small fraction of the carbon in every living thing is the unstable isotope carbon-14, is a quantum event with no fixed, predictable moment of occurrence. Each of these is, by the honest reading of the mathematics, a branching point. Estimates of how many meaningfully distinguishable quantum interactions occur across a human body in a single second run into numbers so large that comparing them to anything in ordinary experience stops being useful, the way comparing the number of atoms in your body to the number of stars in the sky stops being useful. Because both numbers are simply beyond what a human brain evolved to intuit. The honest, humbling answer is that if Everett was right, the version of reality you are experiencing right now is not one continuous single thread quietly moving forward through time. It is one strand arbitrarily selected from your own point of view because you can only ever experience being one version of yourself, inside something closer to an unfathomably vast, constantly proliferating tree, branching at a rate that outpaces every other rate of change we know how to measure. Now let's bring this all the way back down to the alarm clock, because everything I've just walked you through has been building toward one very specific, very personal question, and it's this. Does that mean there's a version of you, right now, in another branch of this tree, who hit snooze when you didn't? Or didn't when you did? And the honest answer requires a bit of care, because it's tempting to picture your conscious decision itself as the branching point, as though somewhere there's a little fork where you, deciding, splits cleanly into two copies. That's not quite how it works, and the real picture is stranger and, in a way, more interesting. Your decision to hit snooze or not wasn't a single, isolated event floating free of physics. It was the output of an enormously complicated cascade, a physical process running through your brain, built out of billions of neurons, each one firing based on electrochemical signals that are themselves sensitive, at their smallest scales, to genuinely quantum-level events. Whether a particular ion channel opens at a particular femtosecond can, in principle, be influenced by quantum uncertainty at the molecular level. That uncertainty doesn't stay contained down at the molecular level either, because biological systems are chaotic in the mathematical sense, meaning tiny differences at the start of a process can get amplified again and again, cascading upward until they show up as differences in something as large and as seemingly deliberate as whether your thumb moves toward the snooze button or the dismiss button. This is sometimes called the butterfly effect, drawn from weather science, where the idea is that an almost immeasurably small difference in atmospheric conditions, in principle small enough to be caused by the flap of a butterfly's wings, can cascade through the chaotic dynamics of the atmosphere and end up being the difference between a calm day and a hurricane 2 weeks later. Your brain and your body, and the choice that emerges from them, sit at the end of an equally long chain of amplification, one that starts down at the quantum scale and ends up, after billions of intermediate steps, at something you experience as a decision. The phrase butterfly effect has a real origin story, and it's worth telling properly because it wasn't a poetic flourish someone invented for a headline. It comes from a meteorologist named Edward Lorenz, working at MIT in 1961, running a simple computer simulation of weather patterns. He wanted to rerun a portion of a simulation he'd already done, so instead of starting the whole thing over from scratch, he typed in a number from partway through the earlier printout to save time. The printout had rounded that number to 3 decimal places, 0,506, while the computer had actually been calculating with 6 0,0506127. Lorenz assumed a difference that's small, about 1 part in 10,000, wouldn't matter. He started the new run, went to get a cup of coffee, and came back to find that the weather pattern in his simulation had diverged completely from the original. Not slightly different, completely different, as though he'd started an entirely separate simulation from scratch. That tiny rounding error, smaller than anything a human being could physically feel or measure in the real atmosphere, had been amplified over and over by the chaotic mathematics governing the system until it changed everything downstream. Lorenz would later use the image of a butterfly flapping its wings in Brazil, setting off a tornado in Texas to describe this. Not because he believed literal butterflies cause literal tornadoes, but because he needed a way to make people feel, in their gut, how a difference too small to detect could cascade into a difference too large to ignore. That's the exact same kind of amplification sitting underneath your decision this morning. A quantum-level difference, immeasurably smaller than Lorenz's rounding error, tucked inside the firing pattern of a single neuron or the timing of a single ion channel, riding the same kind of chaotic amplification through the billions of interconnected neurons in your brain, until it shows up, fully amplified, as the difference between a thumb that taps snooze and a thumb that doesn't. So the branching isn't a single dramatic fork at the moment you decide. It's an almost incomprehensibly vast number of small forks, quantum events happening in your neurons and your environment and the electronics of the phone itself that have been accumulating and amplifying for the entire span of your life. And in enough of those branches, enough of those small quantum differences add up in just the right way that somewhere in this tree there is a version of the physical system that is you, sitting in a branch where the amplification landed differently, and the hand that reaches out does something else. Not a ghost, not a metaphor, a physically continuous, causally connected outcome of the exact same underlying laws of physics that produced the version of you reading this sentence right now. And once you actually understand that the branching is constant, that it isn't reserved for exotic laboratory experiments, but is instead the basic, ongoing texture of everything happening inside your own skull every waking second, the scale of what we're actually talking about starts to become almost impossible to hold in your head all at once. Because if this has been happening at every quantum interaction, in every cell, in every second, for every moment of your entire life, then the number of branches containing some version of you isn't in the thousands, or the millions, or even the kind of numbers we usually reach for when we want to describe something as unimaginably large. It's a number that makes the observable universe's roughly 2 trillion galaxies look almost quaint by comparison. Try to hold this in your hands for a second. There are estimated to be somewhere around 7 quintillion, 500 quadrillion grains of sand on every beach and desert on Earth combined. A number so large that most people simply nod along with it without actually picturing it. Every single grain on every single shoreline on the planet. All of it added together. The number of quantum branching events happening inside a single human brain over the course of one single second is not just larger than that number. It's larger by so many additional zeros that comparing the two is a little like comparing the sand on one beach to the sand on every beach that has ever existed, on every planet that has ever existed. In every one of the branches we've just spent the last several minutes talking about. And that's the branching rate for 1 second. Inside one brain, out of the roughly 7 billion brains alive on this planet right now. Each one running its own cascade, each one splitting its own tree, every single moment. For every moment any of them have ever been alive. We haven't even gotten to the part where this stops being about you alone and starts being about whether you is even the right word for what's branching, or whether the choice you're making has any weight at all if every version of it is happening somewhere, in some branch, to some version of the person reading this sentence right now. That's exactly where we're headed next, and it changes the shape of this whole conversation. Let's start with the you question, because it's not a throwaway philosophical flourish, it's the hinge everything else swings on. When we say there's a version of you in another branch who hit snooze when you didn't, what we actually mean, precisely, is that there is a physical arrangement of atoms, continuous with the arrangement that is currently reading this sentence, sharing every single memory, every scar, every argument you've ever had, right up until the branching point, and differing only after that point. That arrangement is not a copy in the sense of a photocopy, something made afterward, derivative, secondary. It's a continuation, in the exact same sense that the version of you sitting here 1 second from now is a continuation of the version of you sitting here right now. You don't think of your future self 10 seconds from now as a different person just because time has passed and some atoms have shifted around. You think of that future self as you, because the physical process connecting this moment to that one is unbroken. Under Everett's picture, branching works the same way. There isn't an original you and a copy you. There are two unbroken continuations of the same physical system, each one just as entitled to the word you as the other, each one experiencing itself as the only real one. Because from the inside, that's exactly what continuity feels like, whether or not it happens to be the only branch. The philosopher Derek Parfit spent much of his career picking apart exactly this kind of question. What actually makes someone the same person over time? And he built a thought experiment in the 1980s that makes the stakes unusually vivid. Imagine a teletransporter the kind you'd find in science fiction, that works by scanning every cell in your body down to the finest detail, destroying the original in the process and transmitting the information to another location, where a machine reconstructs an exact physical duplicate down to every memory, every synapse, every scar. Most people's first instinct is that this would still be them arriving somewhere else, because the process feels continuous even though the original body was destroyed. Now imagine a small malfunction. The scanner reads and transmits the information perfectly, but this time it fails to destroy the original. You step out of the scanning booth, and somewhere else, a second, fully conscious you, with every one of your memories up to that exact second, is also stepping out of a reconstruction booth. Which one is the real you? Parfit's own answer, argued across hundreds of pages with rigorous care, was that this question is a kind of category error, that we've been assuming there has to be a single. Further fact, a metaphysical thread connecting one moment of a person to the next, when what actually exists is simply a relationship of physical and psychological continuity, memories, personality, connectedness, and that relationship can, in principle, hold between one earlier person and two later people equally well. Neither copy is more the real you than the other. Both are equally, fully continuous with the person who stepped into the booth. Parfit argued that once you really absorb this, the fear of not surviving in cases like this starts to look misplaced. Because what you actually care about when you care about your own survival, the persistence of your memories, your projects, your relationships, your way of seeing the world, is fully present in both continuations. There is nothing further to lose, no extra soul stuff that only one of them gets to keep. This is almost exactly the same structure Everett's branching hands you. Except instead of a science fiction booth, it's happening constantly, silently, at the quantum level, every time a decoherence event splits one continuous stream of experience into two equally real, equally continuous ones. Parfit was writing decades before most philosophers had connected his teletransporter thought experiment back to quantum branching directly. But the two ideas fit together so cleanly that it's hard to imagine, at this point, discussing one without the other. This is a genuinely different claim than the one people usually picture when they hear the words parallel universe, and it's worth being precise about the difference. Because there's a second, entirely separate argument for why infinite copies of you might exist, and it comes from cosmology rather than quantum mechanics, and it's easy to blur the two together in a way that muddies both. If the universe is spatially infinite, and there's genuinely serious evidence pointing that way, based on measurements of the universe's overall geometry showing it to be flat within a small margin of error, then given a finite number of ways matter can be arranged in any given volume of space, the exact arrangement of atoms making up you, this body, this brain, this room, must repeat somewhere, at some distance, simply because you can't have infinite space with only finite arrangements of matter inside it without those arrangements eventually recurring. That argument produces other yous too. Physically identical copies living out physically identical lives at distances so enormous the number itself stops being sayable in any ordinary sense. But notice how different the mechanism is. That argument is about space being big enough to repeat a pattern. It says nothing about branching, nothing about decisions, nothing about decoherence. A copy of you produced that way isn't a continuation of the specific decision you made this morning. It's simply an independent, coincidental repetition of the same physical pattern, sitting somewhere so far away you could never reach it, even at the speed of light. in a universe that started with its own separate Big Bang's worth of causal history, sharing nothing with you except the coincidence of atomic arrangement. The quantum branching we spent all of tonight's first half building up to is a completely different animal. It isn't a coincidence happening far away. It's a direct, causal, unbroken continuation of the exact physical system you are, happening not across some unreachable gulf of space, but right here, in the same room, in the same second, diverging only at the level of which quantum outcome got amplified into your neurons. Cosmologists sometimes call these different pictures different levels of multiverse, and it's worth knowing that distinction exists. If only so, you never confuse the strange, distant, coincidental copy sitting billions of light years away with the much stranger, much more intimate branch sitting 1 femtosecond away from the version of you reading this sentence, sharing your entire life story up until a moment ago. Keep both of these pictures separate in your head as we go, because it's tempting to blend them into one vague, comforting fog of infinite versions of everything, and the actual argument tonight is sharper and stranger than that fog, precisely because it isn't relying on unreachable cosmic distance to do its work. It's relying on something happening inside your own skull, right now, closer than any galaxy could ever be. It's worth pausing here to address the objection that's probably forming in the back of your mind, the one that goes, why should we believe any of this branching is actually happening rather than physicists simply inventing a convenient story to avoid admitting they don't understand measurement? It's a fair question, and the honest answer involves one of the strangest, most rigorously tested results in the history of physics. A result that didn't come from Everett at all, but from a physicist named John Stuart Bell, working in 1964. Bell wasn't trying to defend many worlds. He was trying to settle, once and for all, a question Einstein had raised decades earlier, whether quantum mechanics might just be an incomplete description of a deeper reality. One where particles secretly carry definite, hidden properties all along, and the appearance of randomness is only a reflection of our ignorance of those hidden properties. The same way a coin flip looks random only because we don't track the exact force and angle of the flip closely enough. Bell worked out a precise mathematical inequality that any theory built on such hidden local properties would have to satisfy, no matter how clever the hidden variables were, and then physicists went and tested it, most famously in a series of increasingly rigorous experiments through the 1970s, 1980s, and on into the 2000s, involving pairs of entangled particles separated by enormous distances. Every single time, without exception, the results violated Bell's inequality, exactly as standard quantum mechanics predicts, and exactly as no theory of local hidden variables ever could. This matters enormously for tonight's conversation, because it rules out the comfortable escape hatch, the idea that superposition is just a placeholder for some hidden deterministic mechanism we haven't discovered yet. The universe, at the deepest level physicists have been able to probe, really does behave the way the equations say, genuinely undetermined until something forces the issue. Genuinely, physically split between outcomes in a way no hidden clockwork can account for. Whatever is actually happening underneath, whether it's Everett's branching or Bohr's collapse, or something nobody has thought of yet, it is not simply randomness masking a deeper, single, definite reality. That door has been closed by direct experiment repeatedly for half a century. There's one more piece of evidence worth knowing about. Not because it proves Everett was right, nothing does that with absolute certainty. but because it comes from an entirely unexpected direction, the world of computing. And it's the argument a physicist named David Deutsch has spent much of his career making. Deutsch, working at Oxford, is widely credited as one of the founding figures of quantum computing, and his interest in building an actual quantum computer grew directly out of his conviction that many worlds is correct. Here's the reasoning, laid out as plainly as it can be. A quantum computer doesn't process information the way an ordinary computer does. One bit at a time, flipped definitely to a 0 or a 1. It uses quantum bits, called qubits, that can exist in superposition, 0 and 1 at once. The same kind of superposition we talked about with the radioactive atom and the cat. When you link enough qubits together and run a calculation across all of them simultaneously, the number of computational states being processed at once grows so explosively that certain problems that would take an ordinary computer longer than the age of the universe to solve by trying every possibility one at a time, become solvable in a reasonable amount of time. Deutsch's argument is that this speed-up has to be coming from somewhere physically real. If a calculation with 300 qubits is genuinely exploring more possible states simultaneously than there are atoms in the observable universe, and this is not an exaggeration, the number of possible states for a few hundred qubits does exceed the estimated number of atoms in the observable universe, then something has to be doing that exploring. And Deutsch's answer is that the computation is being carried out in parallel, across many simultaneously existing branches of reality, each branch handling a slice of the workload, with the final answer emerging from the way those branches interfere with each other. The exact same kind of interference Thomas Young saw in his two slits, just harnessed deliberately instead of stumbled upon by accident. Not every physicist who works on quantum computing agrees with Deutsch's interpretation of why the machines work. Plenty build and use them successfully while remaining agnostic or skeptical about many worlds specifically. But the machines themselves are real, increasingly practical, and steadily improving year over year. And the plain fact that this technology only works because of superposition, the same phenomenon underlying everything we discussed in the first part of tonight, means the strange branching world Everett described in 1957 is no longer just a thought experiment argued over at conferences. It's quietly becoming the operating principle behind a new generation of machines sitting in research labs and, increasingly in commercial data centers, being paid for, funded, and improved specifically because the strangeness works. To make that number of states feel less abstract, consider that a modest quantum processor with just 270 qubits, a size that some research labs have already built working chips around, is capable of representing more simultaneous computational states than there are estimated atoms in the entire observable universe. Not more than there are atoms on Earth. Not more than there are atoms in every star in every galaxy we can see. More than every atom in all 2 trillion of those galaxies combined. A machine sitting on a lab bench, cooled to a fraction of a degree above absolute zero, running a calculation that touches more distinct configurations than physical matter fills the visible cosmos. If that calculation isn't happening across genuinely separate, simultaneously existing branches of reality, Deutsch's challenge to anyone who doubts many worlds is straightforward. Then where, physically, is it happening? Standard quantum mechanics gives you the right answer to problems these machines solve, but it doesn't, on its own, tell you where the computation was actually carried out. And nowhere in particular, it just works, has never been a satisfying answer to a physicist trained to ask where the actual physical process is unfolding. Many worlds gives that question a home. Whether or not you find that persuasive, and plenty of extremely capable physicists don't, it's a genuinely different kind of evidence than a thought experiment about cats in boxes. Because it comes with a working, shippable, increasingly commercially valuable machine attached to it. Now here's where the physics stops being able to answer the question on its own, and philosophy has to pick up where the equations leave off. And it's the question that probably started nagging at you the moment I said the word branch back in the first half of tonight. If every outcome happens in some branch, then did you actually choose anything? This is where the conversation about many worlds runs headlong into one of the oldest, thorniest problems in all of philosophy, the problem of free will. And it's worth being honest about how old this problem is, because it didn't start with quantum mechanics, and it isn't going to be solved by it either. Long before anyone had heard of a wave function, philosophers were already arguing about whether a universe governed by strict cause and effect, one event mechanically causing the next, all the way back to the beginning of time, leaves any room for genuine choice. If every event is caused by a prior event, according to fixed laws, then, in principle, someone who knew the complete state of the universe at any moment, and knew all the laws perfectly, could predict every single thing that would ever happen afterward, including everything you would ever think, want, or do. That idea is called determinism, and it's been debated since at least the ancient Stoics, who argued that fate governs everything. And it took a sharper, more mathematical form in the 18th century through a thought experiment proposed by the French mathematician Pierre-Simon Laplace, who imagined a vast intelligence, capable of knowing the exact position and momentum of every particle in the universe at a single instant, and argued that for such an intelligence, nothing about the future would be uncertain at all. That the entire history of everything that will ever happen would already be, in principle, computable. Laplace wasn't making this up out of nowhere either. He was drawing out the full implications of Isaac Newton's laws of motion, published a century earlier in 1687. Laws so precise and so successful at predicting the movement of planets, cannonballs, and pendulums that they gave the entire educated world of the 18th century a picture of the universe as something like an enormous clock, wound up at the beginning of time and simply ticking forward ever since, every gear turning exactly where the previous gear forced it to turn, with no room anywhere in the mechanism for a genuinely open moment, a genuinely uncaused choice. For a long stretch of history, this clockwork picture felt less like a philosophical position and more like an obvious fact about how a well-ordered universe had to work. And it's part of why the philosophical problem of free will felt, to a lot of thoughtful people during that era, less like an open question and more like a slow-motion tragedy quietly playing out underneath everyday life. Everyone believing they were choosing while secretly, mechanically, only ever doing the one thing the gears had already determined they would do. Quantum mechanics complicated Laplace's picture because it introduced genuine randomness at the smallest scales, outcomes that aren't determined by any prior state, only assigned probabilities. But randomness isn't the same thing as freedom, and this is a distinction worth sitting with carefully because it's the exact spot where a lot of popular explanations of this topic go wrong. If your choice to hit snooze was determined entirely by prior causes, you didn't choose it in any meaningful sense, it simply happened, mechanically, like a row of dominoes falling. But if your choice was instead the result of a genuinely random quantum event, a coin flip at the smallest scale of reality, that's not freedom either. A choice made by a roll of dice isn't a choice you're responsible for any more than a choice made by rigid mechanical necessity. Either way, something other than you, in any sense that feels like it should matter morally or personally, appears to be doing the deciding. Determinism and randomness turn out to be a much less comforting pair of options than people expect when they first reach, for at least it's not predetermined as a way of rescuing free will. It's worth being fair to the other side of this debate before moving on, because compatibilism isn't the only serious position philosophers hold, and treating it as the obvious answer would be misleading. A smaller but genuinely serious group of philosophers, sometimes called libertarians in the metaphysical sense, a completely different meaning of that word than the political one, argue that compatibilism concedes too much, that a choice fully determined by prior causes, however much it flows from your character, isn't really a choice in the full sense that matters. Because your character itself was shaped by causes you never chose, your genes, your upbringing, 1,000 accidents of circumstance stacking up long before you had any say in the matter. On this view, genuine free will requires something more, some point at which a person can act as what philosophers sometimes call an uncaused cause, genuinely originating a new causal chain rather than simply executing one that was already set in motion. Nobody has ever identified a physical mechanism that could actually do this. And it sits uneasily next to everything modern physics tells us about causation, which is part of why it remains a minority position, but it's worth naming honestly rather than dismissing. Because it captures a real intuition many people have. The sense that being fully explained by your history isn't quite the same thing as being free of it. Tonight isn't going to resolve a debate that's occupied professional philosophers for centuries, and it shouldn't pretend to. What it can do is show you why the physics, whichever side of this debate feels right to you, doesn't actually make the problem worse. The branching itself doesn't introduce anything new into this old argument. It just makes vivid, in a way nothing else quite does, how many times over the same fundamental question keeps getting asked, at every single scale physics has ever looked at. This is the exact problem that a philosophical position called compatibilism was built to address, and it's held in various forms by a significant portion of philosophers who work on this question professionally, including some of the most respected names in the field. The compatibilist argument goes roughly like this. When people ask whether you're free, what they actually care about in ordinary life isn't whether your decision was the inevitable output of prior physical causes. It's whether the decision came from you, meaning from your own values, your own reasoning, your own character, rather than from some external force overriding those things, someone holding a gun to your head, or a chemical compound hijacking your judgment, or a hypnotist's suggestion planted without your awareness. On this view, a decision can be both fully caused by the prior state of your brain, your memories, your desires, everything that makes you specifically you, and fully free, in the sense that actually matters to human life, because it flowed from your own authentic character rather than being imposed on you from outside. Under this reading, branching doesn't threaten free will at all, because free will was never really about whether the universe could have gone a different way. It was always about whether the way it went came from you. One of the clearest ways to feel the difference compatibilism is pointing at comes from a thought experiment developed by the philosopher Harry Frankfurt in the 1970s, built around the idea of what he called higher-order desires. Frankfurt asked us to imagine two people, both addicted to the same substance, both physically driven by the same compulsive craving. The first person hates the addiction, wishes desperately they didn't want the drug, and takes it anyway, overridden by the craving against their own better judgment. The second person is also addicted, feels the exact same physical craving, but has, at some deeper level, come to fully endorse it, to want it, to have no internal conflict about the fact that this is simply who they are and what they do. Frankfurt's point was that these two people, despite having identical physical compulsions, are in completely different relationships to their own actions. The first person is not acting freely in any meaningful sense. They are being dragged along by a desire they themselves disown. The second person, however determined their behavior might be by brain chemistry, is acting in accordance with what they actually reflectively want. And there's a real, meaningful sense in which that person's choice belongs to them in a way the first person's doesn't. Even though, from the outside, a scientist watching brain scans might not be able to tell the two cases apart at all. This is the texture compatibilists are pointing to when they talk about freedom being compatible with a fully caused universe. It was never really about whether some outside force could have made the atoms move differently. It was always about whether the desires driving the action are ones you'd endorse if you stepped back and looked at them. Ones that feel like they belong to you rather than ones imposed on you from outside or from beneath, by a compulsion you yourself reject. And in every branch of the tree we've been discussing tonight, whichever way the quantum dice happened to land, the version of you making that particular call was drawing on the same reflective, endorsing relationship to their own desires that you have right now, turning this exact idea over in your head. That's not a diminished form of freedom. Frankfurt's argument suggests it might be the only form of freedom that was ever coherent to begin with, in any universe, deterministic or not, branching or not. There's a practical thread worth pulling on here, too, because Frankfurt's distinction isn't just an abstract philosophical tool, it maps directly onto how regret actually functions in a person's life. And it might be the most useful thing tonight has to offer if you're someone who tends to replay old decisions with more harshness than they deserve. Most regret isn't really regret over the decision itself. It's regret over what the decision seemed to reveal about you. The fear that choosing badly in that one moment meant something permanent and damning about your character. But Frankfurt's framework suggests a gentler and more accurate reading. The version of you that made the call you now regret was reasoning, at the time, from the values and information and exhaustion level that version actually had. Endorsing that decision in the moment the same way you endorse your decisions right now, with the same imperfect, human, doing the best it could machinery running underneath. That doesn't erase the consequences of a bad call. Consequences are still real and still have to be lived with and, where possible, repaired. But it does mean the harshest form of self-judgment. The idea that a single decision exposes some fixed, irredeemable flaw at your core doesn't actually hold up against what we now understand about how a decision gets made in the first place, whether you're thinking about it through Frankfurt's lens or Everett's or both at once. You were never a fixed thing being tested by that moment. You were a branching, evolving pattern, doing the best a tired, limited, present tense version of yourself could do, and the next branch, the one you're standing in right now, gets to reason with everything that version learned from watching how the last one turned out. And in every single branch, the version of you making that decision was making it for reasons that felt, from the inside, like genuinely their own reasons, weighing genuinely their own values, in a moment that felt, from the inside, exactly as open and undetermined as this one feels to you right now. The branch where you hit snooze wasn't the you version making a mistake while some other, more disciplined version got it right somewhere else. Both versions were you, reasoning as well as you were capable of reasoning in that moment, given everything you were carrying at the time, and both decisions were, in the fullest sense the word can carry, authentically chosen. There's a piece of this story that deserves to be told with real care, because it's easy to reach for as a dramatic flourish, and it deserves better than that. Hugh Everett's daughter, Elizabeth, grew up in a household where her father's abandoned theory was, by all accounts, something between a private joke and a genuine, if unconventional, comfort to him, this quiet conviction that in enough branches, things worked out. Elizabeth struggled with serious, long-term mental health difficulties for much of her adult life. And in 1996, 14 years after her father's death, she took her own life. In the note she left, she reportedly asked that her ashes be disposed of in the trash, so that, in keeping with the many worlds interpretation her father had spent his career defending, she might, in some other branch of reality, wake up. It is one of the most quietly devastating footnotes in the entire history of this idea, and I want to be careful here. Because the point of mentioning it isn't to romanticize what happened to her, or to suggest that the physics offers any kind of genuine comfort in the face of that kind of pain. If you or someone you know is struggling with thoughts like that, please reach out to a crisis line or a mental health professional. People who are trained to help in ways a video about quantum mechanics simply cannot. The reason this story belongs here, told honestly rather than dramatically, is because it shows in the starkest possible way how much weight ordinary human beings, even the family of the man who invented this theory, have wanted to place on the idea of branching reality, how badly the possibility of another version, a better version, an escaped version, can be wanted. And it's worth sitting with the fact that the theory itself, honestly understood, doesn't actually offer that particular comfort. Because the branch where things go differently isn't a rescue for the branch where they don't. Both branches are equally real, running in parallel, neither one able to reach into the other and change anything about how it unfolds. Whatever relief exists in this picture, and I think there is some, has to come from somewhere more grounded than the hope of a different outcome elsewhere. Let's go back to the alarm clock one more time, because that's where this whole idea needs to land, and it's been sitting in the background through everything we've just covered. Picture that hand again, reaching out in the dark. If you're being honest with yourself, when you actually stop and examine what that moment felt like from the inside, it didn't feel like watching a movie, waiting to see which button got pressed by some force outside your control. It felt like you, weighing things, tired, wanting 5 more minutes, aware you had somewhere to be, running some rough, half-conscious calculation about what the cost of 5 more minutes would actually be this particular morning. That feeling, that texture of deliberation, wasn't an illusion painted over some deterministic or random process happening underneath. It was what that process is, from the one vantage point capable of experiencing it, which is the vantage point of being the pattern doing the deciding. Compatibilism isn't asking you to pretend the neurons and the quantum events aren't there. It's asking you to notice that the neurons and quantum events weighing your actual values and your actual tiredness and your actual sense of what the day requires is not something separate from you making a choice. It is you making a choice. The branching doesn't remove the person from the process. It just reveals that the process was always running on physical machinery. The same way it revealed 200 years after Thomas Young shone light through two slits that the machinery running the whole universe was stranger than anyone expected. And here's the part of this that I think is actually the important part. More important than the raw scale of the numbers, more important than the branching count, more important even than the philosophical resolution of free will. If somewhere in this unfathomably vast structure there's a branch where you hit snooze and a branch where you didn't, the branch you're actually living in right now, this one, the one where you're listening to this sentence, is not somehow the fake one, or the lesser one, or a consolation prize compared to some more real branch elsewhere. It is exactly, completely, entirely as real as every other one. Nothing about its reality is diminished by the existence of siblings you'll never meet. Think about that river again, the braided one, splitting into dozens of channels near its delta. Every single one of those channels is carrying real water, all the way to the same ocean. None of them is a shadow of the real river. They're all the real river, just running through different ground. You are not competing with your other branches for the title of the one that actually happened. You already are the one that actually happened, in the only sense that word has ever meant anything to anyone standing inside a single, unbroken thread of experience. The version of you that exists in some other branch, having made the opposite call this morning, isn't living a life more true than yours, or less true than yours. It's living a life exactly as true, exactly as weighted, exactly as full of its own version of tiredness and hope and small daily calculations as the one you're living right now. And neither of you will ever get to compare notes, and neither of you needs to, because the comparing was never the point. There's a question that tends to surface right about now, when people first really sit with this idea. And it deserves a direct answer rather than a dodge. If every choice happens somewhere, doesn't that make the choice itself pointless? If you're going to hit snooze in one branch and get up in another no matter what, why does it matter which one you actually experience? It's a fair worry, and it's worth taking apart carefully, because it rests on a hidden assumption that doesn't survive close inspection. The assumption that the point of a choice was ever located in its uniqueness, in the fact that it was the only thing that could have happened. Think about a piece of music for a second. A particular recording of a particular symphony played by a particular orchestra on a particular night is not made meaningless by the fact that the same symphony has been performed thousands of other times, by thousands of other orchestras, all technically playing the same notes. The specific performance you're listening to right now through your own ears in this exact room is not competing with every other performance for the title of the one true meaningful rendition. It simply is the one you are experiencing, and that is the entire basis on which it matters to you. Not its uniqueness in some cosmic ledger, but its immediacy, its presence, the fact that you are the one hearing it. The branch you're living in works the same way. It was never going to matter, because it was the only branch. It matters because it's the one you're in, the one your entire felt experience is built from, moment to moment. And that kind of mattering, the mattering of being lived rather than the mattering of being singular, turns out to be sturdier than most people expect once they actually test it against their own experience rather than against an abstract fear about cosmic insignificance. Philosophers who study what's called anthropic reasoning, the question of how the fact of our own existence and observation should shape what we expect to find true about the universe, have pointed out something related and worth sitting with, which is that the question, why do I find myself in this particular branch, having this particular experience, rather than some other one, may not even be a well-formed question in the first place. Every version of you in every branch asks that exact same question about their own branch with equal justification, and every single one of them is, from the inside, correct to feel that their experience is the one that's actually happening to them. There isn't a you floating above all the branches, deciding which one to drop into and wondering if it made the right pick. There's simply the version of you that exists in this branch, asking this question, in this room right now. And the asking itself is already proof that this is the branch you get, because it's the only branch you could possibly be asking the question from. There's a strange comfort hiding inside that last idea, one that's easy to walk past too quickly. Every version of you, in every branch this tree contains, is having some version of this exact experience of being the one who's real, the one whose morning coffee tastes like something, whose tired eyes are the ones actually seeing the room. None of them are cheated out of that experience by the existence of the others, because having an experience was never a competition for a limited resource. It isn't like there's one pool of realness being divided up among all the branches, thinner and thinner the more of them there are, so that a universe with 1 trillion branches leaves each one only 1 trillionth as real as it would have been alone. Realness doesn't work that way, and it never did, not for branches, and not for the ordinary fact that 7 billion other people are. At this exact moment, each one just as convinced as you are that their own life is the one actually happening. Your neighbor's experience of their Tuesday morning doesn't dilute yours. It never occurred to you that it would, because you already understood, long before tonight, that everyone's experience is fully their own, running in full, undiminished parallel to everyone else's. Tonight has simply asked you to extend that same understanding one level further, from the people around you to the versions of yourself you'll never meet, running in branches you'll never see, each one just as full, just as felt, just as entitled to call this the real life, as the one you're living right now. Hold on to that thought, because it's going to matter more than the raw physics does by the time we get to the very end of tonight. There's a particular kind of quiet that settles over a person when they actually let this idea sit instead of just nodding at it and moving on, and it's worth naming, because it's not the quiet of feeling small, though it can start out that way. Every one of us, at some point, has replayed a decision, turned it over at 2 a.m, run the alternate version in our head like a movie we can't stop watching, the job we didn't take, the person we didn't call back, the sentence we didn't say. There's a particular kind of grief tied up in those replays, a grief for a life that, as far as we've always assumed, simply never got to exist. What tonight has actually been arguing, carefully, with the full weight of experimentally confirmed physics behind it rather than wishful thinking, is that the grief might be aimed at something that isn't gone. Not gone in the sense of comfort, not gone in the sense that you can reach it, call it up, apologize to it, borrow from its outcome, but gone in the sense of erased, extinguished, never having happened. No, that version is out there, living in a branch decohered so completely from yours that it will never, under any physically conceivable circumstance, reach back and tell you how it turned out. And there's something almost unbearably tender in that, once you actually let it land. Every road not taken is still being walked by someone with your exact face, your exact memories up until the fork, making the best of it in their own branch, the same way you're making the best of this one. You were never choosing between existing and not existing. You were only ever choosing which existence you, specifically this exact continuous thread of awareness, would get to experience from the inside. And that choice, small as it felt, tired as you might have been when you made it, was never trivial. It was the entire, singular, unrepeatable event of you becoming this version of yourself instead of that one, both real, both happening, and only one of them yours to live. It's worth saying plainly what this does and doesn't change about tomorrow morning. Because it would be easy to walk away from tonight either paralyzed by the scale of it or oddly detached from your own choices, as though none of them carry weight anymore since every option gets taken somewhere. Neither reaction actually fits what we've covered. The version of you in the branch where you get up on time still has to live through the meeting that version is rested for. The version of you in the branch where you hit snooze still has to live through the rushed, frazzled version of that same morning. Nothing about the existence of the other branch changes what it feels like to be the one you're actually in. And nothing about it should. You're not choosing on behalf of some abstract population of yous scattered across a tree you'll never see the shape of. You're choosing the way you've always been choosing on behalf of the only version of you whose experience you'll ever actually have, which is this one, right now. And that was true before you heard any of this, and it stays exactly as true afterward. What changes, if anything changes at all, isn't the weight of the choice in front of you. It's the weight of the ones behind you, the ones you've spent years quietly grieving as though they vanished completely. They didn't vanish, they branched. And the branch you're standing in, the one where you're hearing this sentence, was never the runner-up. If any part of tonight made you think about a specific fork in your own life, the job, the move, the person, the thing you said or didn't say, tell me about it. Not the outcome, not whether it worked out, just the moment itself, the half-second where it could have gone either way. I read every one of these, and I want to know what your version of the alarm clock looked like. Think back to where we started, that half-second before the thumb even touches the screen, both futures sitting on top of each other in the exact same space. That image hasn't changed since the first minute of tonight. What's changed is everything you now know is actually happening underneath it. The double-slit, the wave function, the cat that was never really just about the cat. Everett arguing alone in a room in Copenhagen, the drop of ink that never finds its way back into a single concentrated point. The qubits doing more work than there are atoms to hold them. The braided river carrying every one of its channels all the way to the same ocean. None of that was background trivia. It was the actual machinery sitting underneath a moment you've lived through 1,000 times without a second thought. Whatever it was, wherever it left you, you're here, in this branch, listening to this sentence, and that was never the lesser outcome. It was simply the one you get to live all the way through, from the inside, for as long as this particular thread keeps running. And there is nothing about any other branch, anywhere, in any direction, that makes this one worth a single ounce less than it already is.